Yes, you are audible. Very
Yes.
well audible. Nice, clear sound. No problem at all.
Okay, thank you, sir. So another thing that I would like to say is please be free to stop me at the moment that you're not able to hear me or something, or you have any queries. So I'll just share my screen and then we can move ahead with the talk. Is the screen visible to all of you?
Yes, it is visible.
Yes. So the IIT Bombay houses a nanofabrication facility that has been established quite long back in the Department of Electrical Engineering. So here, this facility was started by a group of few faculty members headed by Professor Zuzair Wasi, and which was followed by many faculty members from many different streams joining in, which now results around, we have 60 faculty members from all over departments of IIT Bombay, which are using this facility. So to move ahead, the flow of my talk would be, I would be talking about the deposition tools that we have, the oxidation and annealing furnaces, the lithography systems, the etching tools, the characterization tools, the miscellaneous tools, the policies that we follow, and how can we use the facility, how can you avail this facility. So to start with, basically, Professor Kiran had actually given me an overview of the participants. So keeping that in mind, I have tried to summarize all the details. Taking into account that this talk is based on MEMS, I'll start with the basic fabrication step, that is the diode processing. And then I'll go ahead where and which places do we require what facilities and what are the facilities and their optimized standards at IIT BNF laboratory. So as you can see on the screen, I have just explained a schematic of the diode fabrication processing, where we start with the basic silicon wafer, which is followed by oxidation. Here, our oxidation comes into picture. We have few furnaces. We can either deposit the oxide or we can grow the oxide. So I'll go into more details in the flow of the talk. Followed by oxidation, then we need to go for lithography. So lithography means what we'll do is, in that case, we will we'll spin a photoresist onto the substrate. We expose it to a specific UV light, due to which the resist either hardens or it softens. And depending on that, what structure we need, we do the development. After that, we need a metallization. So I'll also be discussing on few metallization tools, followed by, again, lithography tools or maybe some implantation tools. To start with the deposition tools, we have a series of deposition tools which fall under the category of physical vapor deposition as well as chemical vapor deposition. So here I have shown pictographically what tools do we have, and I'll quickly give a summary of what tools and what is the basic principle behind them. So let us start with ICP CVD. As you can see in the first corner, that is ICP CVD system, which is an inductively coupled plasma chemical vapor deposition at IIT BNF. So in this ICP CVD system, all of you must be aware that it is a chemical vapor deposition, in which what happens is there is creation of plasma, and there are various chemical reaction processes that occur in the plasma with the chemical species, and you get thin films that are deposited. The tools that are put up on this slide currently all have all are vacuum tools, and all have a base pressure of around minimum 10⁻⁻⁶. So all the processes that are carried out in these tools, they are all done with a minimum vacuum of 10⁻⁻⁶ torr. Now, as we move ahead, you can see the PLD tool, that is the pulse laser deposition tool. what happens in the pulse laser deposition is we have laser pulses that hit onto the target material. So your target material is something that looks like a tablet, and it is placed in front of the laser beam. So what this laser beam does is it comes and just hits the target, and what happens is that the target is sputtered. There is also plasma in the system. So that sputtered vapor material, it mixes with the plasma and forms something that is called as plume. This plume then moves towards the substrate with the applied bias and gets deposited onto the substrate. Now, PLD, it is a very unique and a special technique. Why so? Because you might have known about many normal, the basic deposition techniques that we have, thermal evaporation or the sputter system. So PLD, the thing is, it has advantages over the other techniques in the sense it can be used for complex ceramic material deposition, mostly like the high TC superconductors or magnetic materials. Now here at IIT BNF, what we call it as IIT Bombay Nanofabrication Facility, we have 4 PLDs. You might find during the course of my talk that we have the same tools which are maybe repeatable, or we might have 2 evaporators or something. That is because we have dedicated tools due to the anti-contamination policy that we are following. So in that case, we have 4 PLD systems. One which is dedicated only for silicon. The second, it is only for 3-5 semiconductors. And the third, it depends for, maybe you can use it for metals. And fourth one is open for users. So that was used under the INUP program, which I'll be giving a glimpse at the end of my talk. So why is it an open access and not a controlled or restricted access? So IIT Bombay Nanofabrication Facility is not restricted itself to only, the fabrication thing. We are open up to allowing users to use the characterization facilities only or the deposition facilities only, depending upon their requirement. So mostly in PLD, if I hope most of you must be aware about it, and most of you must be used also the PLD setup during your due course of research. So as I said, PLD is mostly used for magnetic material or ceramic materials. So these kind of materials, those are not easy to directly purchase from the market. Mostly these materials are chemically synthesized in some of the labs. And the result of those chemical synthesis is mostly powder form. Now, once you have this powder which you have made in your lab, okay, so then you need to make a pellet out of it, which is also known as the PLD target, which is similar to something that looks like a kerosene tablet. So we need to make a pellet. So for that, now, the thing is, IIT BNF, when it was initially when it came into existence, so we had few deliverables. So that time it was a CMOS specific laboratory, and hence the contamination policies and the rules were based on the CMOS grade materials. So we are still the main important part of our contamination policy is we do not allow sodium and potassium into the lab, since they are lifetime. So the lifetime decreases. What we do is sodium, potassium materials are strictly prohibited in IIT BNF lab in most of the tools. So when I say the PLD4 is open for uncontrolled access, it means you can use the materials which you have synthesized in your college, your labs, or anywhere. You can use that target or that tablet into PLD4 and do deposition based on that. The only thing that will take care here is whatever material that you have synthesized, your ceramic material or magnetic material, we would check it for sodium and potassium contamination. So how do we do that is, I'll talk during the due course of anti-contamination. So we check for sodium, potassium contamination. If it is found clear, we allow your material to be mounted into the PLD chamber, and you can go ahead just the thin film deposition. Thin film deposition itself is a very great area of research, and PLD forms a significant part of it. So it is not just restricted to fabrication, but we also have been looking into projects that are only dealing with thin film deposition using different tools. So PLD4 is open and it is uncontrolled access provided it follows the anti-contamination protocol set up by IITB NF. Moving ahead, we have ALD tools. We have two ALD tools. One is with load lock and one is without load lock. So the thing is, in ALD, all of you must be aware. I'll just give you in short what ALD does is, ALD uses reactive chemistry, which gives us thin film, one atomic layer at a time. So it has a inductively coupled plasma that allows very low temperature ALD deposition. It is a self-limiting process, and it has high conformal deposition with high aspect ratio. How does this happen is, it consists of various gases precursors. So if you have a material to be deposited using ALD, you will have this combination of many precursors. So what happens is you have this chamber that is in high vacuum, and then you sequentially send this pulses of gases, which are also precursor gases. And that is sent in some fixed amount. So those gaseous precursors, they react with the substrate by themselves in a self-limiting process till the entire material is utilized, which gives one monolayer at a time. Very, very, very high quality of deposition, or you can say self-limiting reaction. Then after that, we ensure that whatever precursor we have sent initially, that is purged out. So to ensure that, what we do is we purge in an inert gas, mostly argon, and ensure that the remaining precursor, which was earlier purged in, moves out. Then we send the second cycles. So ALD basically gets its deposition in a series of cycles, which is called as a half cycle in the first part and a complete cycle. So there are these cycles of ALD, which gives you one monolayer deposition at a time, and you get a very high quality of your thin films. So at IIT Bombay, we have a few materials that I'll show in my next slide, which we deposit, mostly TiO2, or we can go Al2O3. Now, as I have explained you, this process is not that simple. Hence, ALD has its own restriction on the thickness limitation. And at IIT Bombay, the limitation for ALD tools is 15 nanometers of deposition, 1.5. That is the restriction, or that is the maximum thickness that can be deposited one time using our ALD tools. Moving on to the next one, we have a hot wire CVD that you can see on the left-hand side below corner. So this hot wire CVD system is a chemical vapor deposition system, and this was indigenously built up by IIT Bombay students. It was from scratch. So how does this work is, it is almost similar to any CVD system. It has 4 different chambers, which are dedicated for 4 different materials. And as the name suggests, you have a tungsten filament, which is heated to a very high temperature. And then you purge in the required gases for chemical reaction. Since the tungsten filament is heated to a very high temperature, what happens is the radicals or the gases that go inside, those react with that due to the high temperature. They, they split up into the radicals, and they react among themselves and gets deposited or adsorbed onto the surface. So this is how the hot wire CVD works. And we mostly do polysilicon deposition, or we go ahead with silicon nitride in hot wire CVD at IITB NF. Next you can see is the RTP tool. The RTP tool is nothing but the rapid thermal processing. Now, mostly when I started my talk, I said we'll be dealing with the deposition tool. So RTP, if we look at it in a wide sense, it is not exactly a deposition tool. But I have put it here because at IITB NF, we use it not only as an annealing system, but also as a growth tool. So in RTP, what happens is the temperature rises to a few hundreds of degrees in a matter of few seconds. and then you do the processing. So now what happens is this tool is mostly used after implantation. Okay, so that is one use. Then second use is, suppose I have a silicon oxide, or sorry, I have a silicon wafer. I need to grow a very thin oxide for some tensile oxide thing. So, or I need a very thin layer of around few nanometers, say 5 to 15 or 12 nanometers. So RTP is the best tool. You send in oxygen gas, and once RTP is done for that silicon wafer, what you get is a result as some oxide which is as thin as 5 to 12 nanometers. So I've put it as an growth tool also. Moving on to the next slide, there are a few other deposition tools also that we have, or I would not say deposition, maybe deposition and growth is the appropriate word. So we have molecular beam epitaxy. Here also, as I said, we have different tools that are dedicated for different materials. So here also in molecular beam epitaxy, we have 3 MBs dedicated for 3 different category of materials. In MBE, what happens is, it is mostly used for the growth of single crystals. So for example, you can consider any single crystal, maybe silicon, germanium, gallium arsenide. The deposition takes place in a way, or the growth, you take a very thin substrate of a highly crystalline material. Then you have guns that are called as effusion cells. These effusion cells, they heat your material to be grown at a very high temperature, and this effusion cells give out those gases, materials onto the substrate which is already at high temperature at regular intervals. In that case, what happens is the molecules react with the substrate and give you a very high quality of crystalline grown material. So in that case, we have 3 molecular beam epitaxy setups which are dedicated for 3 different groups. One is for silicon, one is for 3,5, and one is for germanium. So next we move to plasma immersion ion implantation. So ion implantation, if you look at it the complete way, ion implantation itself forms a great part of physics, and it is used for many experiments, right from your nuclear to your material modifications to nanostructure formation. So here normally we use this plasma immersion ion implantation at IIT Bombay is also indigenously developed by the IIT Bombay students. And here this is a very shallow implanter. So here you can get implantation up to a maximum implantation depth of around 150 nanometers. That is how it is optimized. And this was a very old system which was developed some around 10-12 years back. Now, recently we have also purchased a new plasma doping system, which is now in use, and we are still setting the baseline recipes. So this is also used for implantation purposes. This is the overview of all the deposition tools and capabilities that we have at IIT Bombay. So what are the materials that can be deposited, and what are the substrates that are allowed, includes the deposition temperature, gases, and the substrate size. So if you move from the second column, top to bottom, if you see so in hot wire CVD, what you can see is we can go ahead with the deposition of intrinsic polysilicon, boron doped polysilicon, and silicon nitride. Allowed substrates are only silicon and quartz. The deposition temperature is mentioned, and the gases are also mentioned, and the maximum substrate size is also given for your reference. Same is for PLD. So PLD, actually, I would not say that this table covers all the materials that we use at IIT Bombay, but we have tried to put in few materials. There are a series of materials that are allowed and used. I'll give you the link also, and I'll show you the details where you can find all the available and allowed materials. Moving ahead with ALD, we have hafnium oxide and zirconium oxide. So as I said, you have 2 ALDs. So one is dedicated only for hafnium oxide and zirconium oxide. The second one has TiO2, TiN and ALN apart from the available materials. Moving on to ICP-CVD, we have undoped polysilicon, silicon nitride, SiO2 also. Then we have MBE that is used for epitaxial growth. Then we also have RTP that is used for ultra thin silicon oxide growth. We have the PDS doping system and PIII that is also a doping system. Then, as I had shown you in the process flow, the second step, if you see, oxidation. Okay, so oxidation is very important. Sometimes it is used as a sacrificial layer. Sometimes you need a tunnel oxide. So in majority of the fabrication steps, the next step immediately after your RCA cleaning forms your oxidation. So we have many furnaces which are not only dedicated to oxide, but we have also some doping furnaces. We also have some annealing furnaces. So this part of the slide will give you an overview of what are the furnaces details that we have at IITB NF. So we have 2-inch furnaces, and I'll go in order from the column wise. So we have dry oxidation and wet oxidation. The difference is we have an oxidation furnace. When we talk about a dry oxidation, you have a silicon wafer that is in the furnace tube, and it is heated at a very high temperature. What happens is then you purge in or you send in the oxygen gas, and this oxygen at very high temperature reacts with silicon and helps in growth of silicon oxide. But dry oxidation has only oxygen, and the growth is very slow process for silicon oxide. Hence, for dry oxidation, you will get a thickness that is up to maximum of around 250 microns of SiO2 layer using dry oxidation. If we move to wet oxidation, the process is quite similar to that of dry oxidation. Considering the only difference is, along with oxygen, we also put in water vapor. How it helps is it acts or it speeds up the growth, and you can get an oxide up to 1 micron. But there is a significant difference between the quality of oxide that you get using dry oxidation and wet oxidation. Dry oxide is always preferred for gate oxide or something, whereas if you are not much keen on to the oxide quality, or you just need a sacrificial layer, you can go ahead with the wet oxidation. The time required for both of them, however, remains the same. The only difference is the thickness that you get during the two processes. Then we have a separate nitrogen annealing furnace, which is dedicated only for nitrogen annealing. Then we have a CMOS FGA furnace that is forming as annealing. Then we have a general purpose FGA. Now, like I explained for PLD, we have a separate PLD4, which is having an uncontrolled axis. Similar is the purpose for this furnace. So another same example I would give in the similar lines, that is mostly when you do some kind of deposition. So most of the, I would say, deposition tools or the film quality is amorphous. So in that case, if you need a crystalline film quality, you need to anneal your films. So for that, you require a furnace annealing. In that case, in this general purpose FG annealing, we have a separate tube that is called as organic tube, wherein you can use your outside samples or samples which are not, maybe the deposition is not carried out at IIT Bombay also, but you need an annealing setup. So in that case, you can use this general purpose annealing furnace. We have a dedicated tube. So similarly, we have N-doped silicon and P-doped silicon using furnaces. Every furnace has a wafer capacity of maximum 25 wafers at a time, 2-inch wafers. Now here we have tried to summarize. SiO2 is a very crucial step in our fabrication. So we have tried to summarize. You can do SiO2 deposition as well as growth. Both the techniques I have been explaining in the past few slides. We have only put here or categorized it into form of growth, that is mostly the oxidation part, because in oxidation, your wafer is partly used up to grow the oxide. Whereas some tools like maybe sputter tools, where you have an SiO2 target and the SiO2 deposition takes place. So the difference is, when I talk about growth, it will utilize or it will partly take up your wafer and give you an oxide, and deposition, you will have an oxide target which will just be deposited. So these are all the tools and their specifications that I've discussed in the past slides. So we have an RTP. So it gives from the 3 nanometer to 20 nanometer. Then we have dry oxidation. We have wet oxidation. We have a sputter tool, which is a deposition tool. We have ICP CVD, which we have discussed. We also have a dielectric sputter, which is also a deposition tools, and we also have these furnaces where you can deposit the where you can grow the SiO2. So as you can see here, I have written here, mentioned specifically Ultec dry oxidation furnaces. So Ultec furnaces have 4-inch wafer capabilities, whereas what we have discussed in the earlier slide was only 2-inch wafer capabilities. Then I move ahead with the metal deposition. So the thing is, if you look at it in the fabrication stepwise flow, then I guess you should have a fabrication tool, like maybe an photolithography tool that comes into between. But the flow is, I'll go ahead with the deposition tools. So as we have different dedicated tools, the deposition tools are mostly the metal deposition. What I'm talking about is for contacts. So here we have categorized this broadly into 3 categories, that is sputtering, electron beam evaporation, and the thermal evaporation. So everyone must be here familiar with the thermal and the E-beam evaporation. It is a very, very old and very nice tool which gives you a very good quality of metal deposition. But then comes our sputtering tool. But every tool has its own limitations and advantages depending on what do we want to use it for. For example, quickly I'll tell you, thermal evaporation is something that you have a boat kind of structure and you have your substrates that are placed on the top of the that boat, and the material is heated in the boat, which evaporates and gets deposited onto your substrate. Similar is the E-beam evaporation. The only difference is here you heat the boat by resistive heating. Electron beam, you use a beam of electrons to heat your materials. Sputtering is something that you sputter your materials and the material gets deposited. So as you can see, we have summarized here the evaporation techniques, be it thermal evaporation or E-beam evaporation. These are very good for liftoff. It is very simple technique, reliable, consistent. But if you have some feature means some pattern kind of thing, it will not give you a step coverage. It will not cover. It will just deposit a very good quality of film with liftoff. Then, whereas if you go for the sputtering, it will not give a very good liftoff, but it will give you a very good step coverage. It will cover all the areas where you have your pattern also. So here we have different tools which are repeatable but which are dedicated for different materials, which I will be showing in the next slide. We have your thermal evaporator, that is for metals. We have multi-crucible electron beam evaporator. We have the metal sputter, dielectric sputter, Orion sputter, and these are the tool capabilities. So we have a thermal evaporator that is only dedicated for aluminium. We also have a thermal evaporator that is dedicated for chrome gold evaporation. Then we have a 4-target E-beam evaporator where you can deposit all these materials. The sputter Orion, AMAT AL. So AMAT, actually Applied Materials Lab, had sponsored IIT Bombay Nanofabrication facility, and they had taken a part of the lab, one area where they had dedicatedly set up their lab for 8-inch manufacturing process, CMOS structures. Over a period of time, the lab became more and more utilized for research purposes, and hence the lab was limited only to the usage of 2 to 4 inch wafers. So this IMAT tools are still there. You might, it will be there all around in the top. Somewhere you'll be able to see etchers are also there. So these are dedicated only for 8-inch wafers. Now moving to lithography system. So lithography is, how do we do lithography? We have tried to explain in a very nice way here, in very simple way. So this is what you have: a substrate, the first image that you can see, a substrate and a material. This is what you want, a patterned material onto the substrate. What we do is we coat the material with a resist, which is also called as a photoresist, and then we expose it to UV light. After exposure, you develop it. So what happens is, let me go to the second part, the resist coating. The resist is nothing but, it is a kind of polymers that we have, and these are special kind of cross-linked polymers. The properties are light dependent. Hence, always what you will see is the lithography is carried out in the yellow rooms because they are very sensitive to light. So what happens is, every resist can be either a negative photoresist. It goes into much detail. So there are negative, positive photoresist. To be explaining it in a layman terms is, you have two kinds of resist. One which hardens when exposed to light. Second, it softens when it is exposed to light. So we coat the wafer using the resist. We deposit your material, we coat the wafer using the resist, and then we do the exposure. So when you do the exposure, the area where you want your deposition.
Excuse me, ma'am.
Yes.
Ma'am, I have a question. Why we need this hard, that is this hard and soft type of material like this?
Resist you are talking about, right?
Yeah. Yes, ma'am.
Yeah, it will come in my slide, and the next slide. After next slide, if you're still not clear, please redo, ask your question again, okay?
Okay.
Yeah, okay. So this is something that I want, okay? Now here, which means I need to protect this part, this small squares that you are seeing. So what I'll do is, I'll coat it with the resist, and I will do the exposure with a particular resist I'll coat. So what happens is, after exposure, whatever part I need my structure, that will get hardened. So once it gets hardened, the material below it is protected, because that hardened part will protect the thin film or the target material that is below that resist, which is hardened now. Now, once the resist is hardened, what you do is etching. So after lithography, you have a significant step that is called as etching. Etching means it is a kind of solvent, which is a mixture of solvent. So it is called as etchant. So suppose I have this yellow, I can say a gold film. Okay. Then I have this resist, red color. After exposure, it has become this blue part, which is now hardened, and it is going to protect that area exactly which is beneath that resist. What I do is, now I put it in a gold etchant. What the etchant will do is, etchant will remove all the gold that is seized onto the substrate. Since you have this blue color ka resist here, that gold which is beneath that resist will be protected, because the etchant will not be able to see that gold. The resist is protecting that gold. Then, as the etchant removes or dissolves the remaining gold, what you are left with is this structure that you can see. You have the blue hardened resist, and you have the yellow gold, which is now patterned. Now, what we need is this structure. We just need a silicon substrate that you can see, a blue one, lighter blue, and you need on top the patterned gold. So what we will do is, this resist will now put in acetone after this fifth step. And once you put it in acetone, the resist will go away, and you will get this patterned structure. So this is one kind of etching. Okay. So now suppose if I have structures here, okay, and it is a very complicated structure, then you can also go for lift-off. So etching and lift-off are two processes. So when you do lift-off, it means you deposit some material. Okay. Then when you expose it, the part where you want the material to be staying along goes away, and the remaining part has the resist and the material. Let me show you one slide which will give you an idea about the lift off process. Okay. Yes, okay. So this will give you an idea about the question that you have asked. So this is a thin film material, the green one that you can see. What you do is you coat and pattern the photoresist. Okay. Then you etch the remaining film. So the green color goes away, and then now you remove the photoresist. This is etching, what I've just explained. Now, when the other type of photoresist will be used is this part, lift off. Okay. What you do is coat and pattern. So here you want the deposition here. So here you will be using that photoresist, which after development will soften and go away. So after development, this part will soften and it will go away. Then you will deposit your film and you put it in acetone. So this red part, which is the resist now, as soon as you put it in acetone, will lift off. So it is something like this. I can give you an example. You have a square block. Okay. On top of that, you put you have a square. You take a table. You put two square boxes there. Okay, and then you just put a layer of water, and you just take up the square boxes. So what you are left is with the water layer that is on the table, and the square boxes along with themselves lift the water that is on the square boxes. That is called lift off. So this resist lift off the metal film. This is normally used in the cases where we do not have etchant. So there are materials like platinum, which itself is costly, but we do not, it is very difficult to get an etchant for platinum. And if you have it, it is very costly. So for materials like that, we prefer using lift off where we do not have the etchant, or getting an etchant is costly. Does that answer my question? Answer your question?
Yes, ma'am.
Okay. So I'll just go back to this process. Then how do you do the patterning? Now, when you move to the patterning, you have two kinds of lithographies, basically. One is photolithography, that is used for microfabrication. And then you have EBL, electron beam lithography, that is used for nanofabrication. So basic structure is, for any process, you have the mask design. You make a mask, you design your pattern, then you write the mask, then you expose the same mask on the wafer. So how do you do that is in these steps. You put it with the resist, expose it to the source, and then you develop it, which was there in the lift off thing. So how do you do this process? I will just show by images. Can you see this image which is to your right hand side?
Yes, ma'am.
So there you see a circle here where the cursor is pointing.
Yes, it is in gray color.
Yes, right, exactly. So you have uh, something that is called as a hard mask. So as I said, there are two kinds of lithography that you can go ahead with. That is photolithography, which is in micron range. Then you have EBL lithography, that is in nanometer range. So I'll be very specific. At IIT Bombay, we have both the tools. For photolithography, first I'll talk about, then I'll move to the nanolithography. So when we talk about photolithography, we have something that is called as a laser writer. Laser writer is something that writes a mask. I'll just show you the laser writer. Okay, this is the system. So here you have nothing but a square piece of glass, I can say, and you have iron oxide coated on those glass. What you do is you feed in your design into the computer, which is in line with your 2-inch silicon wafer. You feed that design into the computer, and the laser writer writes mask. Okay. After writing, you get that design printed onto the that square mask. That mask can be reused and reutilized time and again. That is called as hard mask. Then what you do is that square, this gray part, what I have shown you, here remains your silicon wafer. Inside you can see the white part, and on top of this stays your mask, that is the hard mask or the square part that you have just printed. Then using this several lenses, you expose it in UV light. This is your lithography setup, which is called as MJB4 mask aligner. And after exposure, the same process happens that I've explained. The resist hardens, softens, and then you develop it. This is the mask aligner that we have. So when it comes to microfabrication at IIT Bombay, for minimum feature size, what we have here is 5 micron. Below 5 micron, if you have anything, we move to EBL or electron beam lithography up to nanometer range. Whereas if you have something, as it has a lower limit, similarly it also has an upper limit. So the upper limit in that case is 50 microns. So if you have something that is around 50 microns, so every design will have a minimum feature size and it will have a maximum feature size. So minimum feature size, if it is 5, we go ahead with laser writer and MJB4 for your lithography process. If it is below 5, we go ahead with EBL. If it is minimum 50 or it is just the lowest one is 50 microns, you can get it printed from outside, because the laser writer takes up a lot of time to write those mask files. So we have a few contacts, not contact us, we can give you the addresses. So mostly this is done for designs like microfluidic channels, where people do not have such small features. So we get it printed on a transparency sheet, we stick it onto the plate, and we follow the same process. So this is how it goes for microfabrication. Here, these are the tools that we have. We have two MJB4s, which are used for microfabrication or photolithography. We also have a DSA, or that is called as a double-sided aligner. So it is not only used for the top alignment, but sometimes you need to do back etching, especially when you need to release the wafers or something. So that time you need this DSA or the double-sided aligner. So that is used for backside alignment. So that is also part of photolithography. So MJB3 and MJB4 are similar kind of setup. We just have two different tools. Then, as I said, laser writer, what we have is for writing the mask. But here, the laser writer can also do writing directly on your silicon wafer. Why we do not use it to write directly on the silicon wafer is because we already have these three tools, MJB3, MJB4, and DSA for writing, for exposure. So laser writer helps in that sense. Once you write this hard mask, you can time and again use the same mask to just expose the wafer and develop it. So this is all regarding the photolithography. When I say EBL, now you have something that is less than 5 microns, we come to Wraith. Wraith is our electron beam writing or electron beam system, where we can write feature size of minimum up to 40 nanometers. So here our only limitation is whenever you design your mask, it should be such that all the features, including distance between the two features, or we can say pitch, that should be 40 nanometers. So all features should be above 40 nanometers, but below 5 microns. That is the limitation for Wraith. So I can show you here, these are the images. These are MJB3 and MJB4 setups. This is our DSA. Though it is not taken in yellow light, it is in yellow room. The laser writer is also in yellow room. This is our Wraith setup. So Wraith, along with it, has its own SEM. SEM is used for imaging of the sample to check whether whatever features you have written, those are correct or not. This is what I had gone through earlier. So now we have covered deposition, we have covered lithography. Now we move to the etching techniques. So etching, as I said, you can either lift off or you can etch. So you can etch using a etchant. Lift off, everyone is clear. So it is just going to lift off. The resistor is just going to lift off the material. When you come to etching, etching can be done in two ways. So We have dry etching and we have wet etching. What I explained earlier was wet etching, that you pattern the wafer, you develop it, you just put it into some solvent and you keep it there for some time, and the etching takes place. The etchant will dissolve the relevant metal. Now, there are also a few dry etching tools which are called as reactive ion etching tools. So what happens in reactive ion etching is there is chemistry between these gases, which are mostly fluorine, chlorine gases, and those, along with plasma, they react with the material that is to be etched and they etch out the material. So that is how dry etching is carried out. So we have few dry etching tools also at IITB NF, which are summarized in the next slide. So here we have FTSRI, we have ICP-RI, we have plasma etcher, we have AMAT etcher, we have deep RI. So here, these different reactive ion etching tools have different gas compositions and different power bias, so that it can etch out different materials, as you can see. For example, STSRI, you can etch silicon, polysilicon, silicon nitride, and silicon oxide for 2-inch wafers. We have all the recipes that are standard, and we have optimized it for this particular materials, and those are there on our website. Then you have ICP-RI, which are dedicated only for gallium nitride and gallium arsenide. So we have two ICP-RIs in this case. Plasma etcher this is also indigenously built up system at IIT Bombay. So basically it is used only for etching, but this etcher can also be used for etching of few materials. Then you have the AMAT etcher, which is there for 8-inch wafers, and deep RI, it is used for etching of silicon and diamond, and it will give you a very high aspect ratio, and you can etch through and through features. I'll just show you a few images later on how this DRI images are there. Okay, so these are the images. We have the RI system. So this is the STS model. We also have one Centec model, same system. Then this is the deep RI system. The etch rate is 55 microns per minute for silicon. Okay, so now we have covered almost all the things apart from the characterization. So since the the seminar is related to MEMS, I would like to here I've just briefly explained. We have a silicon wafer, and these are how our cantilevers look like. So you have a sacrificial layer, that is SiO2. Then you have an encapsulation layer where you spin coat the SU8. SU8 is also kind of resist. Here the recipe is given. You just please need not go into much details about it. Just all the specs are given of the recipe. Then after that, once you pattern this SU8 resist, you need contacts. So for contacts, we normally use chromium gold. So here we have 20 nanometers chromium and gold, and then you go for a second level litho, which gives you this red pattern that you can see, this structure which looks like. After gold and chrome etching, you'll get something like this. And the final releasing of cantilevers is from below. This is the image of one of the cantilever that is fabricated at IIT Bombay Nanofabrication. So for backside etching, here you will need DSA for alignment, and this is how the cantilevers will be looking after once they are released. This is the imaging is also carried out at IIT Bombay. So similarly, we have fabricated many similar kind of devices. So to name a few, these are few structures that we have fabricated at IIT Bombay. We have the silicon dioxide microheaters. We have microfluidic channels. Then we also have a MEMS cantilever. And this is what I was talking about, through and through edge using deep RI. So you can see the small holes. This is just nothing but through and through edge in silicon. So moving ahead, now it comes to a general part of material and structural characterization. So as I said, we are not just restricting ourselves to the fabrication facilities. But if anybody who just wants to go ahead with characterization of the materials, we are open to just using the characterization facilities also. So we have a AFM facility in-house. AFM is normally used for surface imaging to see the topography of any film. It works in contact mode, non-contact mode, and tapping mode. The sample size what we need would be maximum 2 centimeter by 2 centimeter, and it gives a very good resolution of around in Armstrong range. Then we have an ellipsometer. Ellipsometer is a technique that works on polarization of light, and it is used for finding out the dielectric properties as well as the thickness measurement of oxide materials. Ellipsometer restricts itself only to oxide materials. We cannot do any metal or thin film, any metallic thin film thickness measurement using this. So here at IIT Bombay, we normally use the ellipsometer after oxide growth or after any deposition of SiO2 to check for the uniformity and the thickness of the oxide. Then we have an Olympus microscope that is used for looking at the feature size post development. We also have a contact angle measurement. This is normally used to measure the things like surface energy and surface tension of the sample. It also gives you the properties of that particular material on which you are going to check the contact angle measurement. Then FTIR system. So FTIR system is normally used for finding out the bonding between the different different materials. So whatever you have deposited or any other thing. So we also have FTIR. We have 2 FTIRs at IITB NF. Then we have HRXRD. We can do all this kind of measurements in the sense we can do theta to theta, then we can do maybe reflectivity measurements also, and all the different things like layer thickness, layer composition, or phase or defects calculation can be done using those measurements. We have restricted this HRXRD. We have not restricted, actually the system restriction is you cannot go ahead with powder samples. In that case, you have to drop cast your sample on a thin film in such a way that the powder does not come out. So the only limitation here we have is we cannot go ahead with the HRXRD of powder samples. Then we have an XPS setup. XPS is a very important tool, another characterization tools that gives us the elemental composition of a particular thin film. XPS can be used in different modes. So the XPS that we have currently right now at IITB NF will give you the elemental composition of the thin film that you have deposited or you have used for your research. Also, you can go ahead with calculation of band gap by using some data from XPS. And we also have depth profiling. So in depth profiling, what happens is it will take the surface elemental composition of the particular film. Then you will be bombarding those by using some argon atoms, and then again you will take the elemental composition. Again you will go ahead and you will bombard the film with argon atoms. So depth wise you will be getting the elemental composition of particular material. It not only helps in checking whether you have any contamination in your films, but it also helps in checking the energy values or the binding energies of that particular material. Then we have this Bruker or Dektak profilometer. So it is one of the profilometry technique that is used for measurement of thickness, or I can say feature measurement of the size of feature. So as you can see here down in the image that is shown, suppose I have fabricated a structure that looks something like this. So you have some tunnels or you have some squares here. What this profilometer does is, it is a stylus profilometer. It has a tip which has a very minimum amount of force. The tip will fall onto the substrate. It will just go ahead with the mechanical stylus kind of thing, where it sees a dip or a step, it will go down the same way and it will give you a almost similar pattern of how the structure looks like. So this is mostly used to measure the depth after etching or development. We have another profilometer. So this will give you a very good quality or of a very good control over the measurement. We have one more profilometer, that is the ambiguous profilometer. But the only difference here is ambiguous will give us very good results only if the features are in some hundreds of microns. When it comes to less than that, DECTA gives a better result. Next, we move to UV visible spectrometer. UV visible is mostly used for measurement of band gaps. It can also be done in three modes: reflectance, transmittance, and absorption mode. Absorption is the most commonly used, and it can be used during your process of fabrication, or it can be used other way around also, apart from your fabrication thing. We also have a PL setup. The with this current PL, what we have is we have a standard laser that is 532 nanometer. Earlier we had one more laser, but that is not working right now. So we have now only one laser that is 532 nanometer, and hence we can check for the layer composition and thickness of those specific materials that give us that has the excitation wavelength of around this values. We also have a cross stem sample preparation. So now cross stem is so you to go ahead with cross stem, I would say TEM. TEM is nothing but transmission electron microscopy. TEM is a very high what I can say, very sophisticated technique that will give you very precise results of your nanometer level imaging materials also. So if you have formed some nanostructures that range from suppose 5 to 10 nanometers, TEM is the best imaging techniques that will give you your imaging of those materials. It has very high precision and it has a very good quality of lenses. So not necessary all the time you have materials that give you direct imaging. So there can be powder materials, there can be thin films, and there can be layer or multi-layer thin films. So here you can do your TEM in three ways. One is, it has a very thin copper grade. So if you have a powder material, you have to just dispense it into a solvent. You have to mix it properly and then drop cast that solvent onto the copper grid. You have to let it dry under the UV light for a few hours, and then your sample is ready for imaging. That is for powder. When it comes to thin films, and if you need to see the interface, like how is your interface reacting, you have to do something that is called as XTM, which also stands for cross stem sample preparation. So for that, you need to specifically prepare the sample. It is a very tedious, very time consuming, and very the technique that requires very high patience. So so these are all the tools that are required for just one sample preparation. In the next slide, I have shown how it goes. So you have, this is the tentative flow chart. You have a thin film. What you do is you have this rectangular cutter and you cut very small rectangular blocks out of it. So you can see here 1, 2, 3, 4, 5, 6. So these are rectangular wafers. So this 3, 4 are your actual film and 4, 5 are dummy wafer, because it is a mechanical process that might harm your film. So we take 2 dummy wafers. Then what you do is the 2 wafers, which are your actual film wafers, you glue it using a specific kind of glue. And then what you do is you heat it on a hot plate. So when you heat it on a hot plate, the binding becomes very strong. Then you again put some mechanical pressure and you get this gluing kind of box that you have seen, the green, yellow, and the red one. So those are all glued together. Then you use a cylindrical cutter and you get something that is shown below. So those are cut into form of small discs. Now these discs are nothing but, you can see those small bindi kind of thing, that is the level of cutting of the cylindrical cutter. Then you need to polish it. So you take the lapping tool here you can see the lapping tool. You just put or you stick it on that lapping precision, the top machine that you see, and you grind it slowly onto the paper. So here it requires a lot of patience, and you have to grind it till the thickness goes up to some 100 microns. You measure the thickness, you grind it again. You measure the thickness, you polish it again. So you have to redo this process a lot of times. Once that is done, what you do is you use a dimpler, and that 100 microns you further reduce to some 50, 60 microns. So the film has now become very, very thin, and it is very, very fragile. Once that is done, you use an iron beam to form a eye shaped structure like our eyes. So it is a eye shaped structure that closes, or that covers that your sample is ready for now imaging. Why is that eye-shaped structure required is, as the name suggests, it is transmission electron microscopy. So that eye-shaped structure allows the electron to transmit and give you an overall picture of the images, or sorry, of the interface of the film. So this is the entire setup, and we have this sample preparation technique at IITB Nanofabrication. However, we still do not have a TEM setup. So the TEM is carried out at SAFE IIT Bombay, but we do prepare samples for TEM. So these are overall range of things that we have. So to summarize, we have an ellipsometer that we can measure from 1 nanometer to 100 micrometer. And then we have a DECTAC from 6 to 200 nanometers, embers from 25 to 300 nanometers, sorry, micrometers, AFM 50 nanometers to millimeter sizes. Then we have filmetrics, which is also similar to ellipsometry for thickness measurement from 4 nanometers to 20 microns. EVO SEM to measure or to see the SEM imaging, and EBL SEM 10 nanometer to millimeter range. Then we have few electrical characterization tools also. Few of them are, we have some 5 tools that you have mentioned, but we have more right now. So we have a Phoenix tool, which is a high temperature IVCV tool. We have a Proxima, which is a IV measurement tool. We have a CV measurement Rigel tool, and stress measurement and room temperature IVCV measurement. So these are just the images. I have shown just 2 images. One is a Kitley tool, and then you have one with the thermochuck, full probe station. Now, moving ahead with the miscellaneous tools. So apart from fabrication, we have few tools which might come under the category of miscellaneous, because that do not come totally under fabrication or totally under characterization. So those are, we have our laser engraving system. What happens is we have this laser with very high power, and it cuts through and through to different sheets. So here we can cut, or we can, I would not say cut, we can engrave on polycarbonate sheets of around 1 millimeter thickness, even acrylic sheets or glass slides also. So here we have given the thicknesses that can be engraved. Moving ahead, we also have a wafer bonder. So wafer bonder is mostly used when you need to bond 2 wafers. So for example, we have one wafer and the second wafer, and then you have this bond chuck. So there are aligners. So there are, those have alignment mark from wafer to wafer, and those are then pressed together with some contact force, and you get the bonded wafers. This is how the wafer bonder works. So similar to wafer bonder, you also might need something that bonds wires. So you have a wire bonder that connects from the wires to the different smaller features. So this is how we have a wafer bonder and wire bonder in miscellaneous. Then we also have many things that we have not mentioned for maintenance, like we have the scrubbers, we have different humidity, this humidifier measurements, we have gas line measurements to control. So all those things are also a part of miscellaneous. Next, we move to the anti-contamination policy. We follow the Stanford Nanofabrication Facility methodology, and we have categorized our tool into clean, semi-clean, gold contaminated, and lithoanalytical. So just to give a glimpse, the highest category is clean, where we have all our RCA clean wafers. Then we have semi-clean A, semi-clean B, gold contaminated, and we have lithoanalytical, all the lithography tools or all the characterization tools. So now I move to how do you see the website and all the facilities and where do you find things. So initially when the facility was established, it came up as the Center of Excellence in Nanoelectronics. So it was funded by the ministry and it was placed at two centers. One is IIT Bombay and second one is IISc. So hence the website still has the name of Center of Excellence in Nanoelectronics. It is now called as IITB Nanofabrication Facility. So to have these facilities open up to entire country, there was a program that was laid forward by the ministry, or it was funded by ministry, which was termed as the Indian Nanoelectronics Users Program. So we have successfully completed two phases of the programs, and the program has been very helpful for researchers all over India, because the idea behind this entire thing was, instead of a user, a faculty member writing a proposal, going to the funding agency, dealing with the ministry people, then getting approvals, the basic funda was they would write proposal to the Center of Excellence or the INUP. Through INUP they would write the proposals. It would be checked for technical feasibility and novelty and other factors by a team of expertise and faculty members. And once the proposal is approved, right from issuing a silicon wafer to your complete device fabrication was under the INUP program. It was granted under the INUP program. So this program has been very helpful to all the students, and we are currently we have completed two INUP phases, and the third phase we are expecting shortly. But as of now, since INUP is not in picture, the facilities are open to usage on payment basis. So for that, what you can do is, I'll tell you in the next slide, but I'll just show you whatever I have explained. How do you go and check for those? This is open to all the users. You can anytime visit the IITBNF or the CEN facility. Here you can see online modules. When you click on that, you will see something that looks like this. And when you click on the live equipment status, you will see all the tools that are there in our lab, IITBNF. If you click on any particular tool, for example, your plasma immersion, you will get all the details. What is the make, model, who is the person in charge, what are allowed, what is not allowed, what are the contamination remarks. So you need not log into anything to have access to these things. You have to just open the website. You have access to all those things. Then now, how to use the facility? We are in process of having the online portal to use the facility. Till then, we have our program manager, Dr. Nageshwari, who is in charge of how to use the facility. So you can send your request to her email ID and we'll take it from there. So what are the things that I would like to tell? If you want to use the facility, what are the things that you need to specifically mention? If you need to use only the characterization tools, you just need to tell what is your sample, what are the number of samples, that's it. And which tool you need. Or if you're not even aware which tool would be better for you, for example, you need an imaging tool, but you don't know whether AFM would be better or SEM would be better, or you need to go with them. So in that case also, you can write to us. We are very open and we are here to help you out with that thing. Now, second comes the fabrication thing. So when it comes to fabrication request, we would need further details. So the initial stage, you can just send a mail and we will get back to you with whatever details we need. So this is her contact email ID. This is the website that you can see. And this is my information. Thank you for your time.
Thank you, madam, for your session. We can take some questions here. So participants, if you are having some questions, please go ahead.
Yes, sure.
Good afternoon, ma'am. Am I audible?
Yeah, you are audible.
Yes, yes, you are.
Yeah. Good afternoon, ma'am. I'm working with this cantilever technology, and thank you so much for wonderful knowledge to us to get this fabrication. And all. I have a question regarding that. While we making this thin film fabrication or thin film coating on the surfaces, it is very difficult to get a, proper imaging or proper clarity to the when we, if you want to study more in the surface studies. So from you, how we can overcome that, ma'am?
So if you just need to look at how uniform is your surface, is that what you're talking about?
Yes, ma'am. Yes, ma'am.
So mostly in that case, we would suggest SEM imaging. So there is something that is, if you are looking at a metal film, then we would also suggest. Okay, SEM is the perfect one, or you can go ahead with AFM, which will also give you the roughness in your film along with the topography of the film. So in that case, what you need to do is when you deposit a film, your substrate holder will always have multiple substrate deposition uh, patches, or I can say you can deposit multiple films. So you have to always take a spare film which you can consider for these kind of characterization. So even if it is a spare or a film which even gets you cannot use it further after all these characterization is okay. So in that case you can do AFM and SEM.
Okay, ma'am. Okay, ma'am. Ma'am, is there anything if it is once we done, we will get that film back, or how we can the sample we are getting back, or it will be completely used for your studies
No,
if you
no,
are sending?
you can get it back. See, SEM will not harm your sample in any way, so you can get it back. So for a technique like XPS, it is going to just your sample is going to be completely damaged. So it depends on the technique. You will definitely get back your sample.
Okay, ma'am. Sure, ma'am. Thank you, ma'am. Thank you
Yeah.
so
Hello,
much.
madam.
Yeah.
Hello,
Hello.
hello, madam.
Yeah. Yeah.
Madam, how to measure the coating thickness of cutting tool by using this whatever maybe the instrument you have shown here? The how to measure the coating on the thickness on this cutting tool?
Cutting tool in the sense, sir, can you be more specific?
Madam, we are increasing the reliability of this cutting tool, and
Okay.
then here we are the putting on this cutting tool
Okay,
sometimes.
sir. So what are the
Yes. Then
dimensions
how
of your
to
cutting
measure
tool?
this coating thickness?
Okay, so in that case, sir, we have, if you have a sample that you can give 1 centimeter by 1 centimeter or something, we have cross-sectional SEM also. So we have a sample holder that will hold the your sample in a cross-sectional way. And when you go on, increasing the magnification, you will be seeing two different layers. One will be of your substrate and one will be of the coating. So that way we can measure the thickness.
Madam, my question is again, here suppose I want to measure the thickness. Then I
Hmm.
have this cutting tool and this coated cutting tool. Then
Okay.
how to make this your required size of this cutting tool? This is my
Okay.
problem. How to cut
Okay.
this?
Okay, then another thing that I would suggest is how do you coat the cutting tool, sir? How do you go ahead with the coating? What is the process that you do?
The suppose the chemical deposition process.
Okay, then one more thing what you can do is you can take a smaller piece and you can stick a double-sided tape that is
Okay.
mostly used in the deposition tools, and you can do the coating. Okay, so once that is done, you just remove the double-sided tape. That will give you a step, and you have a step. You can go ahead with the profilometer and just check where the step is there, and that height will give you a thickness of the coating.
अच्छा, ओके ओके. म्हणजे आधी सुरुवातीलाच काय म्हणता की तो छोटासा पीस तो तयार करून
Right.
घ्यायचा, नंतर ना कटिंग कोटिंग करून घ्यायचंय.
Yes, correct. तसंच करायचं.
पण मला नाही, पण ते आता this is one process. But previous, suppose the sandwich cutting tool is there,
Okay.
and I have to measure, and this size it may be the bigger. Then how to do this?
Okay, so sir, for bigger sizes, right now in our lab we do not have anything, but maybe I can help you. You have my email ID. Can you just note down and you can send me the image of your cutting tool? Maybe I'll check on that and I'll reply to you accordingly. Is that okay?
Yes, madam. Very, very thank you, madam.
Yes,
Very
sir.
nice interaction, madam.
Yeah, thank you, sir.
Yeah, good afternoon, madam.
Yeah, good afternoon, sir.
This is Ravi Shankar. I am I have done my PhD and MTech from IIT Bombay only.
Yes.
I just wanted to know now in this situation. Now, let us say this is a situation like pandemic and other things, and the INUP is spreading as wing. Is there any scope or any chance in the future, or we are planning like remote access of this softwares or some simulation software this users can do? Because some of the softwares sometimes we have to come there in IIT and then do. So is there any provision we are thinking on, or is there any lineup thing where they can remotely use the software from wherever they want? Of course, the process will be followed. It should be approved and everything. So is there any such thing?
So, sir, I think INUP Phase 3 has something that is related to remote access. But I guess Dr. Nageshwari is the correct person who will provide you much more information on that.
Okay, I'll communicate with Dr. Nageshwari then.
Yes. Her email ID. Oh, she is here.
Yeah, I know. We work together, so I will talk to her also.
Sir, Dr. Nageshwari is there, so she is also in the call.
Sure. Thank you.
Hello.
Yeah. Yes, madam. How are you?
Yeah, I am fine. How are you all?
Yeah. Good, madam. We are doing good. I'm doing good here.
Okay.
Right now, presently in Manipal University, Dubai.
Oh, okay.
Yeah. So just because some of the processes like are some simulations, many of them they don't have access to the simulation and all, and they will come as a part of this.
Right now, no simulation tools.
Pardon, madam?
Yeah, please go ahead. Yeah.
So no, I'm just talking any simulation tools which can be given a remote access to INUP users across India or something like that. Is there any provision right now? We are
simulation tools, right? So right now, all our students simulation who all are working on the simulation, they are working on remote. Nobody is allowed to come here, no? So everybody has been given access. But outsiders, I am not sure. But you can send a special request so we can discuss with the concerned faculty and we can help you out.
Yeah, sure. So there may be some scope for the student outside also.
Yes. Yeah.
Thank you very much.
Yeah.
Is there any other questions from the participants?
Sir, hello. My one question. Madam, is there any simulation technique for reliability of this cutting tool to increase the life of this cutting tool by using the coating? Is there any simulation technique, madam?
Sir, we will need to know your material. So along with the imaging, can you send the details? We can check and we can get back to you on this.
Okay.
I can help you, Professor Vishnu Sunavale. I know one person, Dr. Dattatreya Parle, who is into the ANSYS, and he can help you in simulation of like coating cutting tools. Okay, I can give you your contact details of the Dr. Dattatreya Parle to you, and you can contact with him. So he can help you out. Yeah.
Yes, sir. Very thank you, sir.
Thank you, madam. He is into the manufacturing. He has done the PhD from